In this video, I'm going to be discussing improper integrals that have infinite intervals, sometimes referred to as improper integrals with infinite bounds of integration. In a calculus class, you learned about definite integrals, and definite integrals have bounds of integration, a and b, of some function f of x dx. The geometric interpretation of this is you have some function f of x, and you have a left bound and a right bound, and we're looking for the area under that curve and above the x-axis. So that's the geometric interpretation of a definite integral that has finite bounds, a on the left and b on the right. Well, with improper integrals that have infinite bounds of integration, we can have one of three different types of situations. We can have, first of all, we can have a situation where our upper bound is infinity of some function f of x dx. And so that would mean, from a geometric point of view, that we have a lower bound a, but we have no upper bound b. And so the area under the curve could just theoretically go on and on and on. Another situation would be where the lower bound a is going towards negative infinity. In other words, there is no lower bound. So we have an upper bound b, but we have no lower bound. And so theoretically, the area under the curve could be infinite. And then a third situation would be where both the lower bound and the upper bound of some function are not defined. And so you've got a curve, and it has area that is not bounded on the left or bounded on the right. These would all be examples of improper integrals. They're improper because we have not defined the lower or the upper bound with finite values. Now, to evaluate an improper integral, so evaluating, we use limits. Our good old friend, the limit. So as an example, if we have an improper integral where the upper bound of integration is going towards positive infinity, we really can't evaluate an upper bound at infinity because we can never be at infinity. So we use the concept of a limit. And you'll remember that the basic idea of a limit is we aren't concerned with what is happening at a point, but as we approach that point. So we want to be able to evaluate this integral as we approach positive infinity. So we're simply going to write the limit as the upper bound b approaches positive infinity from the left. This will be a left-hand limit of the function f of x, of the integral from, from a to b dx. So we're replacing the upper bound infinity with b, and then we're letting b approach positive infinity, and we're approaching it from the left because we have our curve, here's a, and so we would be approaching from the left. Likewise, if we have an integral where the lower bound of integration is approaching negative infinity, we will replace that with the limit as a approaches negative infinity from the right. So this would be a right-hand limit of the integral from a to b of f of x dx. And we are approaching from the right because we have a function We have a right-hand limit b, but we have no left-hand limit, so we are approaching it from the right. And then finally, the third situation is when we have the lower bound and the upper bound of integration are both infinite. In this particular case, we have to break the integral into two separate integrals that look like the two examples we just did. First of all, we'll have the limit as the lower bound a approaches negative infinity from the right of f of x dx, plus then the limit as the upper bound approaches positive infinity from the left of the integral from a to b of f of x dx. As you're going to see, it's going to be very, very important to use proper notation when you're working with improper integrals. It's the use of the notation that really demonstrates that you understand the concepts that are going on as you're working through these problems. The next thing I want to discuss is the idea of convergence and divergence. Convergence or divergence. This is going to be a very important topic, not only with improper integrals, but in other topics that you'll be doing in a Calc 2 class. So just to give you an idea of what we mean by divergence, let's say we have a graph and it looks something like this. And it has a lower bound a, but no upper bound. So this integral would look something like this. We have the integral from a to positive infinity of f of x dx. Well, let's take a look at this geometrically. There is no area under this curve. This area just keeps going on and on and on. As this curve is going upwards, that area is just getting bigger and bigger and bigger. So we would say that this diverges. This diverges, which geometrically it means that the area, is infinite. My pen is going crazy on me. Is infinite. The area is infinite. Get rid of all that stuff. On the other hand, we could have a graph that also has a lower bound a, but no upper bound. In other words, we have a lower bound a, and the upper bound is infinity once again. But in this particular case, the area under the curve is getting smaller and smaller and smaller and smaller. And if there is a finite area, we would say that this converges. So to converge means that the area is finite, which means there is an exact area under the curve. And one of the things that we want to be able to do working with improper integrals is to determine whether the integral diverges, in other words, it has an infinite area, or it converges, in other words, the area is finite. All right, so let's do a couple of examples of this. The first example that I want to do will be the integral from 1 to positive infinity of x squared dx. So we want to write this as the limit as b approaches positive infinity from the left of x squared dx, the integral from 1 to b of x squared dx. And it's going to be important to, again, use proper notation, and it's very tedious, but write the notation properly. Well, we can now integrate this, so this becomes 1/3 x cubed, and we're integrating that from 1 to b. Then the limit as b approaches positive infinity from the left we're going to have 1/3 b cubed minus 1/3 1 cubed. So we're just evaluating the integral. And at this point in time, it would be handy to either physically separate these into two limits, or at least mentally be separating these into two limits. In these examples, I will physically separate these into two limits. So we have the limit as b approaches positive infinity from the left of 1/3 b cubed minus the limit as b approaches positive infinity from the left of 1/3 1 cubed. Now, what are the limits of each of these? All right, so remember, a limit is what is happening as we approach a particular number. So in this particular case, b is approaching infinity. All right, so if we were to actually think of this as being infinity, infinity raised to the third power is infinity. Infinity times 1/3 is infinity. So this whole limit just becomes infinity. In this case, there is no b in here, so this is simply the limit of a constant. This is 1 cubed, which is 1 times 1/3, so we have 1/3. Well, this limit is approaching infinity. This limit is approaching 1/3. We have infinity minus 1/3. Well, if you have something that is infinite and you subtract a third from it, you still have infinity. So the answer here is that this integral is equal to infinity. Our integral from 1 to positive infinity of x squared dx is equal to positive infinity, which means that it diverges. It diverges, and it also means that the area is infinite. The area under the curve is infinite. Let's do another example. In the next example, I'm also going to have the upper bound of integration be infinity, but this time it's 1/x squared dx. So once again, I would write this as the limit as b approaches positive infinity from the left of, and let's just write this as x to the negative 2 dx from 1 to b. This then becomes the limit as b approaches positive infinity from the left, and evaluating this, we raise it to the 1, so it's x to the negative 1 divided by negative 1, which would be better written as negative 1/x. So we have the integral of negative 1/x. This then becomes the limit as b approaches positive infinity of negative 1/x evaluated from 1 to b. And actually evaluating that, we have the limit as b approaches positive infinity of negative 1/b minus negative 1/1. Now again, you can either physically break these into two separate integrals, or you can at least mentally break them into two separate integrals. I will leave it as one integral, but mentally I'm thinking of it as two separate integrals. We have negative 1/b plus 1 here, essentially. So the limit of this term right here, the negative 1/b, now b is getting infinitely large. As the denominator of a fraction becomes infinitely large, then this whole fraction approaches 0. So this approaches 0, and then this is the limit of a constant is always simply equal to the constant. So the limit is 1. What this means then is that the integral from 1 to positive infinity of 1 over x squared dx is equal to 1. Because this is a finite number, we say that this converges and that the area is finite. The area is finite. The area under the curve would actually be the number 1. That is the area under the curve. All right, one more example. And this example will be the integral from negative infinity to positive infinity of 3x e to the negative x squared dx. In this particular case, the lower bounds and the upper bounds of integration are both infinite. So we have to break this into two separate integral problems. We're going to have to break this into the limit as a approaches negative infinity from the right of the integral from a to b, or of 3. Oh, and because we want to, we're letting the lower bound of integration here be equal to a. Let's let the upper bound of integration be some number between negative and positive infinity that will be easy to evaluate. Usually that's going to be 0. So I'm going to let b be equal to 0 here. And we have x e to the negative x squared dx. And then we want the limit as b approaches positive infinity from the left. And so now the lower bound I'm going to let be equal to 0 and the upper bound b. So I'm simply letting the upper bound here be 0 and the lower bound here be 0 of 3x e to the negative x squared dx. Well, now it's time to actually evaluate the integral. So I'm just going to evaluate the integral over here. So 3x, the integral of 3x e to the negative x squared dx is a u substitution problem. If we let u be equal to negative x squared, then du dx is equal to negative 2x, or dx is equal to du divided by negative 2x. So therefore, the integral of 3x e to the u times du over negative 2x will end up being negative 3/2 times the integral, the x's cancel out, of e to the u du. And then actually integrating that, we have negative 3/2 e to the u, which is e to the negative x squared. So that's the actual value of the integral. Both of the integrals are going to be exactly the same. So now I can rewrite this as the limit as a approaches negative infinity from the right of negative 3/2 e to the negative x squared, evaluated from a to 0, plus the limit as b approaches positive infinity from the left of negative 3/2 e to the negative x squared, evaluated from 0 to b. So in this left-hand limit, we're going to have negative 3/2 e to the 0 minus negative 3/2 e to the negative a squared, plus the limit as b approaches positive infinity from the left of negative 3/2 e to the negative b squared minus negative 3/2 e to the 0. Now it's time to evaluate these limits. Again, we could think of these as two separate integrals. So first we have the limit as a approaches negative infinity from the right of negative 3/2 e to the 0. And then this is minus and negative, so that's plus. So plus the limit as a approaches negative infinity of e to the negative a squared. And then breaking these into two as well, we have the limit as b approaches positive infinity from the left of negative 3/2 e to the negative b squared plus minus the negative plus the limit as b approaches positive infinity from the left of 3/2 e to the 0. Alrighty, so let's take a look at each one of these limits. Well, e to the 0 is 1, so this is a negative 3/2, which is a constant, and so the limit of a constant is the constant. Here we have e to the negative a squared. Now what is happening is a is approaching negative infinity. It's sometimes easiest to think of these with a negative exponent. Think of it as 1 over e to the negative a squared. So as a is approaching infinity, you're getting the denominator is going towards infinity. Once again, if the denominator is going towards infinity, this whole fraction is approaching 0. Same thing is happening here. Negative 3/2 e to the negative b squared. And I forgot to put the negative 3/2 in here. That's not going to affect the outcome, but it should be in there. So this is also going to be approaching 0. And then this is going to be approaching 3/2. So what we have here is negative 3/2 plus 3/2, which is 0. Which is equal to 0. So that means that my integral from negative infinity to infinity of 3x e to the negative x squared dx is equal to 0, which is a finite number. And because it is a finite number, that means that this converges and that the area is finite and is 0. The area is actually 0. Which is a finite number. Okay, so that is improper integrals with infinite bounds of integration. There are other types of improper integrals, and I will be addressing those in another video.